Welcome, Dr. Garcia. My name's Luke Briggs. I'm here with Lorenzo, Tim, Madeline, and Critton. And we're going to talk to you today about a potential solution for a next generation transport aircraft. Good. Next slide, Lorenzo. And so the whole process is really going to be following the sort of IPPD approach that we've talked about throughout the semester. And we're going to go through sort of each of those steps to sort of support our final solution that we have come up with. And so the agenda for today is we're going to first talk about establishing the need. We're then going to define the problem and establish what value our solution could provide. From there, we're going to generate and evaluate different alternatives, in which ultimately we'll be able to make a decision and provide a framework for validation and verification in the future. But really getting to sort of the crux, why do we need this? As we all know, climate change poses really a serious global challenge. And with the world agreeing on the Paris Climate Agreement, the airline industry has set pretty high goals for emission reduction, with a lot of different airlines committed to zero carbon emissions by the year of 2050. But at the same time, what we've seen is that there is an increase in demand for commercial aviation, particularly driven by economic growth and the emergence of sort of this worldwide middle class. But what we see is with sort of these two kind of counteracting forces is that in order for the aviation industry to meet their goals regarding climate change and also sort of satisfy the demand by this economic growth, we see that they're going to have to make some serious changes in order to meet sort of both this goal and this demand. And so what we've seen is over time is that sort of the traditional tube and wing aircraft they've served aviation well for the last several decades. As I'm sure you know, Dr. Garcia, but there really are a couple of different drawbacks. They're not as aerodynamically efficient as they could be. They have a high fuel burn rate, and they're not great at incorporating some of maybe the new carbon emission reduction technologies. And so what we're really seeing is that we've reached the performance limit of this old technology, and we need to transition to something new. The key issue with this, though, is that there's a variety of different solutions out there. We have things like sustainable aviation fuel or SAF, we have hydrogen-powered aircraft, and we have these advanced configurations. And each of these are potentially a solution, but they all sort of have their own limitations, drawbacks, and advantages as well. And so we've really been able to sort of get into what are these limitations and what's going to be the best solution for us moving forward. And this is a really important problem overall because there are a lot of people interested in this, from sort of the government authorities like our civil aviation authorities to the airlines themselves, who I said before have set these net zero emissions goals, as well as the passengers, the airports, and the technology partners that make this sort of whole thing fly. And so it's a really important problem. And essentially, overall, what our goal is that we want to design a new commercial transport aircraft, which will, like I said before, enable us, or you, Dr. Garcia, to meet these global demands for commercial aviation while also reducing our climate change impact. And so some of the objectives are really just going to be to, of course, improve that efficiency, reduce our impact on emissions, but also not necessarily require massive changes to aviation infrastructure, which could cost millions or billions of dollars and really aren't a economically viable solution. And so when we get into the concept of operations of our aircraft, they're essentially the same, really, as they already have been from before. We're going to still go through sort of all of those pre-check, warm-up, and taxi and takeoff and everything that follows that. But we really do have a couple of key constraints. And what we really want to be considerate of is we want to have an aircraft that's reliable. It's got to be compatible with our existing infrastructure, and we don't want it to be too economically infeasible. And so we want to keep that cost to be less than an implementation cost of less than $100 million a year. And I'm now going to pass it over to Tim here, who's going to talk about establishing the value for our problem.
Yeah, thanks, Luke. So as Luke the previous slide, the functional requirements are essentially the same as a current existing wide-body tube and wing aircraft. So this next generation transport aircraft needs to replace this aircraft as easily as possible. So things like it needs to be able to operate at the same airport as current aircraft, should be able to unload and offload passengers and cargo within a reasonable amount of time, achieve flight times no longer than existing aircraft, and shouldn't require any significant infrastructure modifications at airports where it operates. Here's an overview of our QFD. I'm not going to go through every room, but I will highlight a few rooms with interesting information. So this first one here being the customer needs. A lot of things here will be no surprise, such as, fuel efficiency needs to increase, aircraft range should increase if it becomes more efficient, increasing lift efficiency, so the aircraft requires less power to operate, etc. Next slide. Engineering characteristics here are related to those needs. So increases in the aspect ratio to allow it to create more lift. Noise is also a requirement, so it needs to reduce its noise. Emissions should decrease. Next slide. Here's a customer assessment comparing a few proposed designs to existing aircraft like the Airbus A350 and Boeing 787. So in the first column, you have the Boeing truss brace wing, and in the far right column, you have the Jet Zero blended wing body aircraft. And you see the blended wing body aircraft performs well in areas such as increasing fuel efficiency, aircraft range, and improving the visual appeal. It is definitely a striking design, as we'll see later. Okay, over to Madeline.
Hello, I'm Maddie, and I will be covering the MBSC portion of our presentation. Next slide, please. So utilizing Magic Draw, we were able to build a systems engineering model of our aircraft. And this here is a organization of the different systems and different subsystems of our vehicle. And next slide. This here is a breakdown of the different requirements. It is a little hard to see, but for each system and subsystem, we were able to attach different requirements or different modifications we thought would be necessary for this aircraft to achieve. Next slide. So this here is a parameterization we have achieved for a model via Magic Draw, kind of like the first step in building a digital twin. So on the top right, that represents a relation between the lift required for the aircraft with inputs of airspeed and air density and altitude and wing area. And below that, on the right, is a relation of the different weights that go into the subsystem or the propulsion subsystem. So your combustor or your nozzle and so and so. And the item on the left is a relationship between the different weights of the vehicle, so we know what our total mass is. And next slide. So we were able to complete two parametric instances. The one on the right calculates what happens if you have a low coefficient of lift for our wings, and the item on the left shows us what happens if you have a high coefficient of lift. So on the left information, we were able to figure out that, hey, with a higher coefficient of lift, we were able to carry more weight and sustain a higher flight time. Next slide.
Thank you, Maddie. So now that we know that we have these requirements that we want to meet, we need to find a way to provide a solution to you, the customer, to kind of accomplish that mission. That could be a very daunting task, as there can be thousands of different configurations available to solve the problem. Therefore, we needed a tool to kind of narrow down the design space. One tool that we used was a morphological matrix, which provides you, the customer, with different characteristics as well as different options. So each design point will be a different selection of these options in the morphological matrix. So looking at our morphological matrix, we're able to create 5 different alternatives for evaluation. The first one was the Airbus 350, as well as a synonymous 787-8, which is very similar. And we found that the current Airbus 350, which is implemented today, does have increased efficiencies, does decrease emissions, but not to the level that we want. We're able to identify this in the QFD. We found that they were long range and fuel efficient, but not enough to be competitive. We also found other weaknesses, such as that the current wide-body airliners are noisy and inefficient. Therefore, we started looking at advanced configurations by selecting a different subset in that morphological matrix. One different alternative was the truss-braced wing, which showed that with its increased aspect ratio, supported by the structures of the trusses, we're able to get a considerable reduction in fuel burn, with one study citing a number of about 74% reduction. However, we found that it would be very difficult to implement this type of solutions, specifically because they might not be compatible with the airport infrastructure that is currently in play. Therefore, we moved on to look at some different alternatives, one being a blended wing body, which sort of acts as a lifting body to get better fuel efficiencies. The current solution on the market is the Jet Zero blended wing body, which is shown to have a 50% reduction in fuel burn and emissions. We also found other advantages to it in the QFD. It particularly serves well in customer assessments based on its look and its sleek design. But there will be some weaknesses such as the manufacturability and general market skepticism to accept this type of solution. This was just 3 solutions, but we did generate up to 5 different alternatives. So next, we needed to evaluate these alternatives. We specifically use a multi-attribute decision-making technique called TOPSIS, which calculates the distance to the positive ideal solution. A positive ideal solution for our case was one that maximizes efficiency, minimizes emissions, minimizes cost, and so on. Therefore, we use this decision-making process, and what we found was that the blended wing body and the truss brace wing ranked really high. However, the Jet Zero blended wing body performed the best overall, even in different subjective weighting scenarios. And as you can see here, it really outperformed in efficiency and emissions, which is what our objectives really focused on. So we went forward with the blended wing body.
Now that we have an understanding of how, through an insightful evaluation, we narrowed down upon our blended wing body plane, it is quite important to go over this chosen concept. Next slide. Our proposed concept is a hydrogen-powered blended wing body, which offers a groundbreaking solution that tackles both the challenges of the increasing aviation demands and the aggressive sustainability guidelines. The Jet Zero blended wing body aircraft offers an unprecedented aerodynamic efficiency, along with which helps wherein the entire body of the plane works as a lift generating device. This is due to the seamless integration of the wings and the body, which was not seen in the conventional aircraft design models. This reduces the fuel consumption, and additionally, we have integrated boundary layer ingestion technology. This minimizes the drag by reusing the airflow that would have otherwise created turbulence. Next slide. On the propulsion front, we have liquid hydrogen, which is stored in cryogenic tanks, which are used to power the aircraft. Now, hydrogen offers twofold advantages. A, it has a higher energy density than conventional jet fuel, and also the burning of hydrogen does not have any formation of CO2, thereby completely eliminating the issue of carbon dioxide emissions. Also, due to the high energy density, this enables extremely long haul flights without the extremely long haul flights. Further, positioning the engine on top of the fuselage significantly reduces the acoustic emissions because the airframe works as a shield of engine noise from the ground, and which is not observed in traditional tube designs. Next slide. However, with this innovation came some challenges, particularly in the structural design area. This structure faces complex load conditions due to its integrated airframe, specifically the cabin pressurization system, which must counteract both the bending moment of the airframe and the internal pressurization forces, creating high risks of buckling. Next slide. To address this challenge, we have incorporated tessellated stiffened grids and multi-bubble pressure cabins, which distribute the stress more evenly and significantly enhance buckling resistance. These structural innovations ensure safety and reliability without compromising on our propulsion advantages and aerodynamic efficiency. So to summarize it, our key features can be kind of seen as on the front of sustainability, it has zero carbon emissions due to hydrogen propulsion. The efficiency enhanced due to aerodynamics, which reduce drag and fuel consumption. There is noise reduction, and for structural integrity, we have added advanced stiffening structures. Now, as we prepare to move into verification, it's crucial to recognize that our concept shows great promise, but rigorous testing will be required.
Okay, so what we did here is construct a requirements verification matrix with the choice of the blended wing body in mind. So the requirements here are listed along with the verification method and allocation for which system it's going to apply to, with the success criteria in the final column. A lot of these verification methods are going to be done by test, others with analysis. Next slide. Here's our verification and validation risk management matrix. Just pointing out one at the top, if the aircraft were to fail to meet the emissions standard requirement, that would be high consequence. So on here, likelihood 1 to 5, 1 being most likely, 5 least likely, and for consequence, 1 being a large consequence, 5 being a small consequence. So we think there's a pretty high likelihood of that emissions requirement not being met. However, we think the consequence is low since the overall design of the aircraft would be more beneficial than not. Next slide. Okay, so that concludes our presentation. Again, we just want to reiterate that we think the blended wing body design is the best choice due to its increase efficiency and lower environmental impact. Okay, thank you.